Find the fewest number of coins required to make 45 cents. In this problem, we are asked to make 45 cents in change. Rather than a penny, nickel, dime, and quarter, we can only use a 27-cent coin, a 13-cent coin, a 6-cent coin, and a 1-cent coin. For this problem, our objective function is to minimize the number of coins where Pi represents the number of coins at each stage, I. Our state variable, x, will be the amount of change left to be made at each stage, and Vi will represent the value of coin I. And Pi is again the number of coins chosen to make change from stage I. From the state equation, we'll assign the constraint x1 equals 45 cents and x5 equals 0 cents, which means we must start with 45 cents of change left to be made, and we must end with 0 cents of change left to be made. We'll subdivide the problem into 4 stages, where I represents the stage, and variable Vi represents the value of the coin at stage I. Using the forward-reaching DP algorithm, we'll start at stage 1, where I equals 1 and Vi equals 27 cents. We also know x1 equals 45 cents. If we create a box diagram, we'll assign the top half to the state variable xi, and we'll assign the bottom half to the number of coins used to make change for stage I, and the number of coins used to make change through stage I. Therefore, for stage 1, we'll determine how many 27-cent coins should be used to make the change. If we use 0 27-cent coins, then we'll set variable P1 equal to 0. Then we still have 45 cents change to make, following stage 1. If 1 27-cent coin is used to make change, then P1 equals 1 and x2 equals 18 cents of change left to be made. The state variable x2 is calculated by subtracting 1 times 27 cents from the 45 cents of change we needed to make at the beginning of the stage. In the forward-reaching dynamic programming algorithm, we start at each value of the state variable x plus 1, which is x2, and ask the question which value, or box, in the previous state should we come from, which will reduce our state variable to 0 cents, yet minimize the number of coins used. For this first stage, there is only one box to come from, so the decision is trivial. Moving on to stage 2, the optimal combination of coins having 0 13-cent coins would have 1 27-cent coin, which makes a total of 1 coin combined, and 18 cents of change that still needs to be made. If there is 1 13-cent coin in the change, then along with 1 27-cent coin, there is only 5 cents of change left to be made. We chose to come from the box with 1 27-cent coin because if we came from the box without a 27-cent coin, there would be 32 cents of change left to be made. If we compare these two states, we notice the left box has a better state variable of only 5 cents left to be made, but the right box has fewer total coins, 1, and our objective function is to minimize the total number of coins. This analysis doesn't help us determine if the 27-cent coin should be in the change or not. However, since the next two coins are 6 cents and 1 cent in value, it would only take 5 more coins to make change with the left box and 7 more coins to make change with the right box. Therefore, we'll choose the left box which includes the 27-cent coin. If our change includes two 13-cent coins, then we cannot include any 27-cent coins, otherwise we would exceed the 45 cents. And the same goes for when there are three 13-cent coins. Now we're ready to move on to stage 3. In stage 3, if the change excludes any 6-cent coins, then we'll want to carry over the combination containing one 27-cent coin and one 13-cent coin, which means we still have 5 cents of change to be made. If we have one 6-cent coin in the change, then we'll carry over three 13-cent coins, which totals 45 cents. With two 6-cent coins, we'd come from the combination with one 27-cent coin. And the same is true if we had three 6-cent coins. In stage 4, we will only display p-values for 0, 5, and 6, because by the end of stage 4, we must pay the entire 45 cents of change. And we only have 0 cents left, 5 cents left, and 6 cents left to pay off, which makes the decision at stage 4 trivial. Since the question asks to find the fewest number of coins required to make 45 cents change, we choose the solution which only requires 4 coins. When reviewing the possible solutions, the correct answer is A. If we want to know which combinations of coins makes 45 cents using just 4 coins, we perform traceback and notice 2 different combinations of coins achieve this optimal value. The first optimal combination includes one 27-cent coin and 3 6-cent coins. And the second optimal combination includes 3 13-cent coins and 1 6-cent coin.